So suppose that you have a system that I label as system 1, and the outside, which is actually the surrounding, all right, and this is the system that we would like to study. Okay, so we may say that actually we have E1, right, and of course that volume 1, like something like that, and then this is at E2 and V2, okay, and they are in thermal equilibrium. At temp T, right? Then both of them are at the same temperature. So basically, well, you could think that when you're taking the whole thing, this is called a universe, right? So this could be treated as an isolated system, right? Your universe. Isolated system, okay. And so the Hamiltonian of the system is given by the total Hamiltonian can be expressed as the Hamiltonian of the system 1 plus system 2 plus also maybe I would say I. This is the interaction between 1 and 2, right? And we could think that this is very weak. All right, so then, well, in some sense, we can throw it away. Very weak. Okay. So the micro canonical density matrix can be expressed as this. Well, this one, which is actually we learned about this last time, right? Okay. If you think this is as a whole system, I mean the whole universe, right? Okay, and let omega E1 be a plot, okay, density for system 1. Have the energy E1 given by this okay. So it means like how much this part of Hamiltonian or the energy contribute to the whole energy of the system, right? That's kind of that P1, P1, and 1 factorial, and EP2, EQ2, into factorial. This is just constant for normalizing, to make things normalized. Okay, so right, and here, no, and here is the density of the whole system, right? But you want to consider only the part of the whole system, okay? So you need to find the avalanche or the probability distribution of that. Okay, only the first system. So from that, I'm going to put thing in the shorthand. This yeah, the volume element. Okay. Okay, and turn that the density to be this one. Okay. And so we say that the whole bunch thing can be expressed as this okay. This is the way that the phi or the function up there. So what in now let's say that E1 star is the most probable value of E1, right, right, which can be obtained by looking at this right. This condition going to give is, so this is basically nothing but a critical, right? Critical value right, of the E, right, to make so once you put the whole thing here, which is actually omega, right, into this relation, and then you do the derivative with respect to the E1. So what you get is okay. So basically, you will get this kind of relation. And then using the fact that the entropy can be expressed in terms of this, right? Then you find that derivative with respect to the E of this entropy going to give you okay. We also using the fact that the total energy of the system is just add them together. So this must be constant, right? Because of the conservation of the energy. So you have, right, then you have actually the chain of the energy. If this increase, this must be decreased or the vice versa, right? So so you apply all these relations. So you could find that. Oh, this should be omega to the. So basically, Okay. And you apply that this kind of relation here, right? So it turned out to be that you're going to have okay. So you have this kind of relation out of after you apply this of this thing, and then this is turned out to be actually the relation of the temperature, right? You get that actually T1. This is give you so what does it mean by having this? This is the thermal equilibrium. Okay. What does it mean by having this relation at the end? So, because then we do all the calculation here with the condition actually the most probable, right? The most probable. So this is going to be the most probable. I would say the most configuration of the two systems. Right. Would be, which is actually, which is indeed is thermal equilibrium, right? If you, I mean, if you have two systems, they are together, and then you let them go with the time, and then finally the system will be reached to the thermal equilibrium. That is the most probable state that you could get at the end, which is actually kind of agree with thermodynamics, right? If you start like, if you, I give you an example of two boxes, the hot one and the cold one, right? Once you put them together, right, as the heat start to flow, right, and then the heat will stop once two of them, both of them reach the thermal equilibrium, right? That is the most probable state or configuration, right, of the system. Okay, this is kind of cool because we get somehow that actually from the inside that actually why your system have to go into this kind of state, right, from this kind of perspective right here. Okay. So we know that the total energy of the system is this one. Therefore, my canonical ensemble of total system is okay. So suppose that actually your energy E1 must be a range between 0 and the total energy E, right? So it's going to compose from this 2 bit, right? Here, right? You can separately decompose this omega into this, but actually this is nothing but the E2. But once you sum all possible E1, then you have to turn the argument into the E1, right? That's it. Okay. So let me so what we want to compute next is rho 1 for a subsystem system 1. Okay. So we start with the definition of expectation value of any quantity A with respect. I put the label here. It means that with respect to the system 1. Okay. So A PQ and you have to okay, right. So where we define law 1 in this way. So it means that you have to trace out all the variable with actually associated with the system 2, right? Out of this the total system, and you left with everything that actually relate to the system 1. This is, you could think that actually the whole the process, this is like a partial trace, right? Out of 2 partial trace, right? You take away the system 2 from the total system, all right? And you left only the system 1. And Okay, you have this. Because this is a definition of the law of the total system, right? Right. And of course, that this could be can be expressed as this one, right? Yeah. So next, we use the facts that suppose that actually the energy of the system 2, which is very large, yeah, compared to the system 1. That is a condition that we're going to take consider. Then we may expand this function. Actually, this you can turn this E1 to be the Hamiltonian one. Yeah. Okay. H1, right? So okay, so this is definition of the entropy of the system 2. From this, you can see that the argument of the entropy is actually expressed in terms of this total energy and the H1. As I mentioned, with this condition, you can do the expansion of this thing. So what you get is that E is 2. Okay, so you have this. And then, of course, this is definition of the inverse temperature, right? So you have this. Okay. And then we use all right. Again, so wow, this is a definition of the inverse temperature. Right. Let's see what we could get from this. Okay. Since so well, actually, this thing can turn into the exponential function 1/k/bt, and so bt, right? Okay, because from this relation here, right, we can do that, of course. Therefore, then, if you divide by this, so you're going to have this relation right here. Then I will be calling the relation of the low one, which is now I define a new function which is called that where this that is defined in this way. And so right. Oh, okay. This so finally so this is your partition function. Not well. Yeah. This is called partition function. Right. Yeah. Okay, let's see first. So now well, we can, after we do some kind of mathematical trick, you could get the explicit form of the row one, right? By having this kind of expression right here. So you have to keep in mind that actually now your whole system consists of system 1 and system 2, which is weakly interact, which it actually can be ignored. We ignore the interaction, right? And then we all do all that we can do all these kind of mathematical steps, and then finally you can express the plot density only for the system 1. Right. Okay. Actually depends on the Hamiltonian of the system one. Right. And of course this partition function, and we will see later the role of this partition function. Okay, good. Then we can take a break. Actually, we can, okay. 5-minute break. Okay, that's fine. Right. Okay. So now all right. So we have this. Okay. Next, we using the definition. Then so we should actually this can be cancel each other, right? So you left with only this E1, and of course that you can turn in case of actually you have the continuous variable, or you can turn summation to be the integration, right? So then, so if you look at this equation, the whole bit here, we should actually the same with this one. So then you can now write the partition function, right? The system in the explicit form. Then and since it is delta function, so it's going to take away this integration and turn this E to be the Hamiltonian. Okay, so we have this. So then we could compute now the entropy of canonical ensemble, right? We should I'm going to use this kind of SC, right, to represent that actually this C coming from the canonical one. Okay. The trace of the row. This one. So I turn KB 1 over KBT to be the beta, right? Okay, and you get this. So basically, no, sorry, too quick. So you get minus KB minus beta, the average of this Hamiltonian, this one. Does that make sense for you? Because if you split this logarithm, right, you could get two terms, and then once this exponential has come with this together, you will get only the factor. This one come down, and then so basically that the average here. I mean the average of this thing is the trace or blow of this thing. Okay, that is the definition. And so the last term, you will get log of the partition function. Okay, so finally, we get the average of the Hamiltonian plus KB. All right. Okay. This is the relation that we have in okay. So once you multiply the whole equation with the t, right? You will get this one, and so this is the definition of internal energy of your system, right? Right. Okay. I'm going to define it as function f, which is Helmholtz energy. Hopefully, energy. Okay. Then with this setup, we find that actually your partition function with this kind of definition, your partition function can be expressed in terms of the Helmholtz free energy. Right. This is V and N fixed, right? Right, yeah. Okay. Let's have a look a bit on the internal energy. So if you, as I mentioned, well, this is okay. The trace is, I mean, the integrate of this one, and then the average of this one, and then you put the row in here, and so you get we should okay. So again, you can compute the internal energy if you know the partition function of your system. So from this, you can see that if you know the partition function of your system, you can compute the internal energy, entropy, and even the Helmholtz-free function in the, right, everything, right. So actually, there is a topic that actually, but I believe that actually you probably learn or the equipartition theorem. You know that, right? If you know that, I'm not going to talk about that because it's a bit basic. Then I'm going to skip it, and then we're going to look at an example. Okay. The example again would be the ideal gas. We should, why is that ideal gas? Because it's simple. Ideal gas. Of course, that's Hamiltonian. Your system. Right. So you can, of course, start from looking at the partition function, right? You should actually okay, where this p square is sum over p square of the all particle, right? So basically, you can see that it's like you do this kind of integration in the power n. Right. So you have n particle, right? So, and then you see that this function doesn't contain q. Then this bit is nothing but your volume, right? I can take it out. So I get b over n, right? N factorial, and what you have left inside is this one over n here, right? And this is very simple because this is a Gaussian one, right? And then after you finish the integration, what you have is this one. If, well, sorry. อยู่ดีก็เริ่มหิวข้าว
กินก๋วยจั๊บไปก่อนนะ
ยังไม่รู้เลยครับเป็นไงผมต้องเอาไปในเมืองด้วยเนี่ยวันนี้ก๋วยจั๊บไหนอ่ะอ๋อได้เดี๋ยวลองชวนหมู่ดู for n is very large, right? You can approximate this, right? You know that that's setting. Right here. If your n is very large. Okay, of course that keep that as a note. So this is your partition function. So if you got that partition function, you can compute the Helmholtz free energy, F, right? Okay, so you get this relation. And so the internal energy going to be this one. And entropy of the ideal gas, while you fix volume and the number of particles, right, is going to give you this. You can check yourself by yourself again later whether that you get the same as I have here or not. Okay. And of course that we should be able to recover the equation for the ideal gas, right? PV equal to the nRT, right? So the pressure can be computed via the Helmholtz free energy with respect to the V. If you fix these two variables, right? This is kind of we learned about this earlier, and it turned out that you get perfectly this is nothing but the ideal gas equation, right? Very beautiful. And then you can compute also the chemical potential, right? This here, of course, that So summary, let's say let's put in a very short way. Summary, if once you have this partition function, you can compute all interested quantity. Okay, that you can, well, this is quite obvious example that actually, if you start from the for sorry the partition function, then you can compute the rest, the thermodynamics quantity. Right. Okay. All right. Okay. Good. So the next topic will be about grand canonical ensemble. Right. Let me see the message. It seems like I have a lot of things. Okay. Let me take some water. All right. Okay. Continue. And so, yep. Shit. Right. Okay. So again, so you have your system 1 with E1, T1, N1, V1, right? And you have system 2, which is E2, T2, N2, and E2, right? This is system 2, this is 1. And then there is some exchanging matter between these two systems, right? Okay. But again, the whole system, I mean, this whole system is isolated. Okay, the whole system means the universe. Right? If we think the universe is nothing but the 1 plus 2, okay? And the n, right? But we going to consider these two limits. We have to keep it in mind. That actually, like your system 1 is kind of very small compared to the system 2, right? That. Again, the Hamiltonian can be expressed as these two Hamiltonian, right? Actually, I can label this as 1 and 2 as well. Okay. And again, so we can, of course, introduce the partition function of the whole system, right? F given T, right? Okay, so you have this. But we actually, again, this is what we are interested. This is what we are. Right. This system 1, right? You can treat your system 2 as a surrounding, right? But this case is quite special because the surrounding system exchange the particle between them, right? Okay. Again, so what you can do, so you're going to write this Hamiltonian in terms of these two. Okay. So you have to take in care this kind of non-distinguishable this factor. Right. And H1 and H2 in this case. So now I introduce a plot density, a plot. Okay. We now introduce a plot density for system 1 to have energy and number of particles N1 and volume V1. Okay. So we have this omega this one too. Okay. And again, so we do the same trick that we look at the critical value of the E1, right, to make this function more probable. Right. Okay. And it turned out to be that again you get this condition. If you do the derivative with respect to the E, you will get the most probable configuration that the two systems will go to is the thermal equilibrium. And so, but if you do the derivative with respect to the n1, you will find out that actually these two chemical potential will be the same. It means that so at the end there is no exchange particle anymore, right? When it leads to that kind of equilibrium state, right? Okay. So well, actually we don't need we don't need to look at the volume. Maybe I think just these two variables maybe enough. Okay. And the okay, this is the definition of the mu, chemical potential. Actually, we got it. So you know how to derive this, right? But I haven't shown you yet how to derive it, but I'm going to keep as a homework to do by yourself, okay? Okay. All right. So, oops, sorry. So therefore, okay. So apart, well, in the canonical case, we taking care only the exchange the energy, right? Now we taking care, we have to care about the exchange the particle between the system as well. Then that is the reason why this function has to be a function of these two variables, and E and N, right? Okay. So then the low one, again, we need to find the row one as we did in the previous case. And again, so once as I give you the condition of the the N actually very small, right? And the E as well, right? Checking again this kind of condition. So what you have so we expand this row, right? What we're going to do is we do this expansion in the entropy. Oh, sorry. In this, no, not this, but in this function. Right. This is definition of the entropy of the second system. And so, of course, once you do the expansion, you will get okay. So it turned out to be that you will get the first term is the same that we have in the previous case, but in this case you have the extra term because the exchange of the n, right? Okay, you have definition of the, this is a definition of the chemical potential, right? The change of the entropy with respect to the number of particle. Okay. All right, so where are we now? So actually, if you look at this carefully, the mathematical step more or less the same, right? But you just, in this case of grand canonical, you just add the extra feature that actually the two systems can be exchange the particle. Then you have the extra term. That's it. All the rest you just follow the same step math. Okay. All right. So all right. So you divide the whole equation by kb, right? So, and then I put this approximation because I'm going to ignore the higher term in the expansion. Then what you have this. Okay. Then once you have this, you could write out your row 1. And I'm going to define this set as a set G. This is nothing but to make to make it different from the previous case, because this is the grand canonical, right? Right. So your set G is this one. And then if you follow more or less the same step of the math as earlier case, so you will end up that actually this could be expressed okay. This is your 30. Okay. And once you get this, so good. Next, we look at entropy. of this GAN canonical, right, ensemble. So the S will be labeled by this G, right? The trace of the row again. So okay, and then at the end, after you do the same trick as we did earlier, so you will get 1/t expectation value of the H1, expectation value of the N1, right, plus this extra term, right, and then you just reorganize the whole equation. You will get right, which is this is the definition of the gland potential. Right. This is the gland. The GAN potential. So in this case, your gland, your partition function for the gland canonical ensemble can be expressed as exponential of this gland potential here. So in the previous case is in terms of the Helmholtz function, right? Here. Again, so we can work out the example for the ideal gas again, but I think I'm going to give you as a homework to work out yourself for this particular case. I mean, GAN canonical for the ideal gas, because it's going to be more or less the same step that we did for the canonical one, but there is some extra feature that you have to take care, like this one. It's another thing, right? Okay, that's it. Okay, so no, actually, I think I'm going to stop here today, because otherwise, I think it's going to take a bit long time. So next time I think I'm going to explain you about black body radiation, which is somehow we need quantum a little bit. I'm not sure that I might start to explain you about quantum statistical mechanics first, and then after that we get back to the black body radiation. Let's see. I need to think about this. All right. Okay. Then we stop here for today, and then I'm going to give you homework by this weekend, and for all right.